Kotlin Multiplatform. So sort of to set this up, I was looking at when I, over maternity leave, I actually was doing some exploration into Kotlin Multiplatform, which has sort of been a buzz in the Android/Kotlin world. And I was actually using the Chicago Roboto conference app as sort of a test bed for that. So basically porting that app to iOS to get some experience and learn a bit more about Kotlin Multiplatform and how it works and sort of the a more practical experience of it. And as I was doing that, I learned a ton, and that was great. And so then I started as we were looking at the brush sharing, or as I was sort of researching that, I actually started the that code sharing experiment in C++, which was fun and working out pretty well, but there were some definite challenges there. And so I thought I'd give it a quick try in Kotlin Multiplatform and kind of see what that was like. And things were going really well, and so I stuck with that for some more prototyping. So today I just wanted to kind of like introduce Kotlin Multiplatform, sort of how it works and why it's different from other multi-platform systems, and yeah, that's it. So I mentioned before, like I was trying it out. So I have several concerns when it comes to like multi-platform stuff. Things like React Native and I don't know, Cordova, like Xamarin, like those other things. And performance is a huge concern, especially when we were talking like JavaScript bridges and like all that kind of stuff of non-native code. Dependence on third parties to update. So, Apple or Android or Google comes out with some sort of like new UI elements, or Swift UI is sort of an example. Like the idea of okay, there's this new thing I'd like to use, but I have to wait for this third party to update their library, so now that I can access it through such and such of an interface. Long-term maintenance, of course, you don't want somebody abandoning something that you base stuff on, and then full team buy-in, which is a concern with anything that affects all of the team like that. So a bit about Kotlin Multiplatform. So Kotlin, the standard Kotlin is Kotlin JVM, and this is sort of what is used for Android and what everyone knows. But there's also Kotlin JS and Kotlin Native, which are two separate things, and I'll get into those a little bit of the details. So Kotlin JVM is like the original Kotlin. Kotlin itself is so the history of it. It's been around, I believe, about as long as Swift, 7 or 8 years, something like that. And it was developed by JetBrains, who makes the IntelliJ IDEs and other tools. And basically, like all of their IDEs and other tools are written in Java. Java has history, and so they so back in 2011 or something, they started developing their own language that they called Kotlin, which is named after an island outside of like St. Petersburg or something. And the idea was it's a language that is a bit more modern than Java, but it compiles to JVM bytecode. Kotlin C is the compiler, and so it compiles down to JVM bytecode. And what's nice about that is it gives you full interop, two-way interop with existing Java libraries, since like at the end of the day, it's all just bytecode. So that means, and that's part of what has powered, like at Google I/O, Google announced that, a couple years ago they added Kotlin as a fully supported language to Android. So that makes it, C, C++, Java is the primary, and then Kotlin. And this year they announced that the Android team is going Kotlin first. And so they're coming out with new APIs that and libraries that are Kotlin only, and like use language features in Kotlin that aren't available in Java. So anyway, part of the reason they were able to do that is because of this full interop. Since it's 100% two-way, which conflicts with what I just said. Since from Kotlin you can access anything from Java without without needing interfaces, translation layers, like all this kind of stuff. The entire community was able to move really quickly to Kotlin, and that's been a huge win, because you don't have to throw away existing code or anything like that. And that's one of the primary values, I guess, of JetBrains as it relates to Kotlin, is that interoperability with other stuff. There are a few, I sort of hinted at it, and I don't know if maybe we'll cover them if there's interest and there's time, but there are a few like newer features of Kotlin that are inaccessible from Java, and those are different things dealing with concurrency and that kind of stuff, and those are implemented like as libraries, as Kotlin X extension libraries. So they're optional pieces, but basically, all of the existing Java libraries that are out there, the existing like Android framework is all zero issues interoperability with Kotlin. Kotlin JS is basically a backend for the Kotlin C compiler, which I'll talk about in a little more detail later, that basically compiles Kotlin to JavaScript. And so this is similar to TypeScript, CoffeeScript, these other sort of like nicer, higher level languages that compile down to JavaScript. Again, it has full interop with existing JavaScript libraries, and that's two-way interop. So that means that the Kotlin code you can import Node packages or like React.js if you use that. You can import that into your Kotlin project and use those. And the other way, if you have Node scripts or client-side JavaScript, and you have a Kotlin library that is, I don't know, an SDK that reaches out to something like Firebase or something like that, your JavaScript code can access everything in the Kotlin side. And this, one of the things that I don't think I included, but I don't have speaker notes here so I can't see, is along with the full interop, which is one of these guiding principles of Kotlin development, the JavaScript that's compiled from Kotlin is fully readable intentionally. So it's compact JavaScript, but it's not like minified. It's not like you have no idea what's there. And that's part of that full interop. That way, if you're importing a Kotlin JS library into JavaScript, you can still have your code completion and see the source and all that kind of stuff. And then you get to Kotlin Native, which is what I've been spending most of, like a good chunk of my time in. And basically, this is an LLVM backend for the Kotlin compiler, which again, I'll talk about the compiler components for that in a little bit. But basically what this means is that the Kotlin code is being compiled using LLVM, just like Swift or C, C++, any of that, into machine native code. It is so the Kotlin native part of this basically, I'll get into detail about this in a little bit. Compiling Kotlin into the LLVM IR. What that allows you to do is leverage the existing LLVM compiler optimizations, and again, full interop with existing native libraries. So this is like super key. And I'll talk, I think, if I can remember my slides, a little bit more about the C interop tool and how that works a little later on. But I want to get into like talking about like how the stuff compiles and works. And so here's sort of a diagram of this is like a common like modern compiler architecture. And this is how LLVM, which is the compiler that is used for Swift and Objective-C. Clang is sort of, I forget where exactly it fits into this, but it is part of the LLVM compiler. But the idea is that you have a front end, you have optimizations, and a back end, In the front end comes, source code in whatever language that might be. It goes through whatever optimizations the compiler chooses to do, which are oftentimes sort of dependent on the architecture of the machine, dealing with little and big endian and different kinds of things like that. And then the back end actually translates that to machine code. So on the front end, it really looks like this. Your Swift code goes into the Swift front end, and that compiles it into this IR, this intermediate representation. The same thing for C code, Kotlin code, and this is how LLVM as a compiler, or GCC, or a lot of these other compilers, are able to support a ton of different languages in the same compiler, is by doing this kind of thing. So that's the front end, and then on the back end, that's the machine specific stuff. So your ARM 3264, x86, microcontroller, Windows, whatever you've got back there, that's where it is. All of the code from the front end, basically what the compilers do is they compile that into IR, which is intermediate representation in LLVM, and that's similar to Java's bytecode. So that's LLVM's representation of the code and the structure and the objects and all of that. It's if you look at it, it looks, I don't know, to me it looks sort of like assembly. Speaking as somebody who doesn't know how to write assembly or use assembly, but it's that kind of like low-level code representation, and the idea is that it's generic enough that any of these source code languages, and LLVM supports far more than these three, but any of these can be represented with IR code, and then optimizations live in the compiler. That way, when you compile Swift code versus C code or Kotlin code, you're sort of getting a lot of the same optimizations. You don't have to reproduce all of your optimizations for the different languages. And then the backends know how to compile optimized IR code into machine-specific code. And that's how all of these compilers also support multiple backends, which it's exciting to think about a time when you would have a specific compiler for a language and for, your, i386 machine or whatever came before that. I'm too young for that. So all of this sort of encompasses the LLVM compiler, and this is how it's structured and how it works. If we look at Swift and specifically, what we talk about as the Swift compiler is really a Swift front end for the LLVM compiler. So it's got 5 different steps. You've got the parse, which parses your code into, it does semantic analysis on that, and then it generates SIL, which is the Swift intermediate language, which is that's something that's super similar to if you've ever done .NET development. They have an intermediate language, which I think is just called IL, or bytecode in Java, like all that kind of stuff, same as IR code in LLVM. And then Swift has its own optimizations that are performed on that SIL code. And then that optimized SIL code is what goes into the Swift front end, which is just a custom LLVM front end for that SIL code. And so these 5 pieces, if you look at the Swift compiler documentation, they actually and the code repo is actually broken up into these 5 components, and then a few other support components. So that's how Swift works. Kotlin works really similarly. The Kotlin compiler follows the same architecture as LLVM. It has, you have a front end, which for Kotlin, just processes Kotlin code. It turns it into its own intermediate language. It runs all of its optimizations on that, and then the way that these Kotlin JVM, Kotlin JS, and Kotlin Native work is they're just custom backends for the Kotlin compiler. JVM was the original backend, which outputs Java bytecode. JS, outputs JavaScript, and then it's titled as Kotlin Frontend on the top right over here because in the LLVM compilers view it is a front end, but to the Kotlin compiler it's a back end. So that's the Kotlin Native. Kotlin Native is just a custom back end for the Kotlin compiler that also effectively serves as a front end for LLVM. And what's important about this is that if we can go back, so this one, Kotlin, goes through here, compiles to, into our Kotlin front end that goes through the LLVM optimization process and everything. Swift does the exact same thing. So effectively what that means is that, these are all going to build. So like the whole non-native code performance concern is basically gone, because what the Kotlin Native compiler doing is it compiles that Kotlin code down to the native code through LLVM, just like Swift code, Objective-C code, or C or C++ code. So performance isn't a huge, there's still things to consider there, but it's not like using JavaScript or something like that. So next up, I wanted to talk about the native interop. I mentioned before that we have the C Interop tool. And what that does is that creates Kotlin bindings to C and C++ libraries. So the Kotlin team recognizes that if you're going to be using Kotlin, as a native language, effectively, Interop has always been super important to the Kotlin team, and that's no different with native stuff. There's a whole history of C and C++ libraries on native platforms, and shared libraries like libpng or libjpeg, all that kind of stuff. And nobody wants to throw that away, which is something you kind of have to do if you're using other tools like React Native or Flutter or other cross-platform tools like that. So the C Interop tool it's a command line tool that they've written that you run on def files. And so def files, which I'll show in a future slide, basically just describes, it's a definition to describe what you want to include in your interop. And then you process that with the C Interop tool, and that produces Kotlin bindings. And Kotlin bindings aren't, they're not like another layer. They're not, an adapter layer or something like that, where you're talking through some sort of like auto-generated Kotlin classes or anything like that. You can think of it as effectively header files. So Kotlin obviously doesn't understand C header files. And so what the C Interop tool will do is produce Kotlin code that is effectively a header file that delegates into the native code. So it's sort of used in the same way, and it just gives you a way to talk to native code through Kotlin. And then, from there you've got those bindings, and then you just run the Kotlin Native compiler on all of the code in there to produce an executable. And once you use the C Interop tool, you get those bindings. You get full code completion, navigation, all of the normal stuff that you expect from an IDE. And then that also works with Swift and Objective-C. One thing I should mention here is that the way that for iOS specifically, well, I guess also Mac OS, the way that Kotlin Native interops, it doesn't interop directly with Swift, and I'll show this in a little bit, but it kind of goes through the Objective-C bridge, and I'll fill more details in on that in a little bit. Basically, there are different, I guess this slide says to produce an executable. You run the compiler to produce an executable, but it's not always executable. Whatever you're producing for interop with like iOS or Mac OS, you would tell the Kotlin Native compiler that the binary that you're creating is a framework. And so what that gives you is the actual binary, like shared object or like whatever it is, the actual compiled code. But then it gives you an Objective-C header file. And so when you're working with, and that Objective-C header file is annotated, and I can't imagine this is anything you do by hand, but it's annotated with, it's just filled with annotations so that when you use it from Swift, it doesn't, aside from some of the limitations with the Objective-C Swift bridge, it doesn't necessarily feel like you're talking to Objective-C. And I'll show some examples of that in a little bit. But moving on, so that whole like C interop thing, you can do that. You can, the def file and all that. You don't have to do that for everything. That's kind of for, if you have, custom libraries like libpng or libjpeg that you're interacting with. But for the native platforms, and the supported native platforms are like, Linux, Mac, iOS, Windows, and Android, meaning the Android C++ stuff, or C and C++ stuff, not the Android Java stuff, because that's not native. For those platforms, platform libraries are included. So as basically there's in the, I should have also added all of the Kotlin stuff is all open source. It's all on GitHub. And so in the GitHub repository is a platform libs directory. And so you can see, for all of, speaking of iOS, for GLKit and MetalKit and UIKit and all of those, they've created the def files. And so those are all sort of just included as part of the native platform. So you don't have to bother doing all of that. Those are included. Custom libraries are supported, but you have to make your own def files, and then that's just part of the build process. And then, for iOS and macOS, this was a huge thing. CocoaPods are supported bidirectionally. So basically, for your if you have shared code in Kotlin, the iOS portion of it, you can import CocoaPods. You can import AF networking or other common CocoaPods, whatever it is. And basically the build process has a way of translating a CocoaPod into a def file and automatically making those bindings for you. So you can, from your shared Kotlin code, you can consume external libraries, like everything that's already out there. You basically don't have to rewrite the whole, history of shared libraries. And that works the other way too. You also, if you're making a shared library, which I'll show you for the conference app that I made, it creates that framework, but you can also effectively have it export a CocoaPod. So the interaction with your project in Xcode or anything like that is you just add a CocoaPod like any other, and you've got access to everything there. And I should mention that this is full screen for me, so I can't see any of you. So like Kyle did, feel free to interrupt if you have questions or anything. Yeah. That's a good question. My guess would be just Objective-C because of the headers that are needed, but I am not sure. Yeah, good question. As far as I know, I haven't, my Swift side knowledge is fairly limited, but I believe that effectively to access Swift from Kotlin Native, I think you do need to have the the Objective-C annotations or whatever. So it has to be accessible from Objective-C. And that is something I know the Kotlin team, they actually move really fast, surprisingly fast. There's quick sidebar here. I think there's purely anecdotally, I want to say like there's new releases every maybe month or two. It's pretty fast. It's really open. So they have a public bug tracker, and then they have they call them keeps. I think from my understanding they're pretty similar to like Swift Evolution, but like there's a repo basically where they have discussion about like language features and different things like that. They accept pull requests from the public and everything, and they have so they have this fully open process for evolving language and support, and they've got a new release probably every 2 months or so. But that being said, they also have a strong deprecation policy, I guess. So it's not like and this is partial outsider's perspective, but it's not like when a new version of Swift comes out and you have to go through and like find all the stuff that's broken in your code because they kind of update stuff without having sort of a deprecation process. And that being all of that is to say that I think in their documentation they do specifically call out that the whole like Objective-C annotation for Swift and all that kind of stuff. I don't know where it is on the timeline, but they do say that is sort of a temporary thing. And I'm assuming that came out of, they basically have support for native code by consuming headers right now because their first priority was C and C++. And so that just sort of gives you Objective-C headers for free. And so I think that's where that came from. But it's all moving pretty rapidly, and they do intend to support Swift directly at some point. I just don't know where it is. So let's take a look at some def files. Just because I wanted to point out how simple it is and a little bit of how it works on a platform specific basis. So this is actually from GLES3. This is from one of the iOS platforms. And when I say one of the iOS platforms, that's because iOS, ARM32, ARM64, and x86 64, which is the simulator. Those are separate things because they have separate binaries. But this is the def file. You just point it at some header files. You give it a filter. The header filter just tells it, basically, it'll import those headers, the gl.h and glext.h, and transient headers. And the header filter just sort of limits that scope. So you're not going to get the whole world of, the C standard libraries and like all that stuff. The package is the output because, in Java and Kotlin world, we work in packages, namespaces, whereas C and C++ kind of does, but not C and Objective-C. So you just give it a package to output to, and then give it some compiler and linker options. And that's it. That's the entire def file. And that will, give you bindings to OpenGL, all of OpenGL. So sorry for the buildup. The dependencies on the native, on a third party to update the native bridge. Because of this, doing it yourself, it means you don't have to wait on the React Native team to integrate some library or anything like that. As a quick anecdote about that, Apple announced Swift I/O at WWDC, and within a couple days there were issues on the Kotlin Native GitHub issue tracker. Not that Swift UI wasn't working, but that it was working. There were just, some sort of like little issue type of thing that people were running into. But the point being, you're like something new comes out and you don't have to wait for somebody else. You can just, give it a def file and make your own headers or bindings and move on with that. So from there, long-term support, JetBrains and Google are sort of the two big ones behind Kotlin. They're contributing a ton, but I think because of Google's issues with Oracle over Java and because of the terrible court system here in the U.S., before they brought Kotlin in as an Android language, they presumably had long negotiations with JetBrains, and so they developed the Kotlin Foundation. So Kotlin is owned by this, independent third party that has board members from, here and whatever. The tooling and everything is all open source. It's all on GitHub. All of the, the issue trackers, the communication, the new commits that are going in, and actually the team is all super responsive. I've had, personal conversations with lots of them. There's a ton of community support. At this point, a lot of it is, the Android community, because that's such a big space that has really gotten behind Kotlin. But as far as multi-platform, Square actually, which I don't know if they're as big in the iOS community as they are in Android. Some teams at Square make open source libraries that are like now part of Android itself, but are the canonical AF networking, the libraries that everybody uses, and so they're making a big push into Kotlin Multiplatform, specifically the Cache app. They're looking they're working on translating a bunch of their open source tools to Kotlin Multiplatform, and they're working on sort of moving their apps in that direction as well. Trello's kind of doing the same thing. They're doing a lot of experimentation with multi-platform long-term maintenance.